Okay. Good evening, everyone. Hope you are safe and healthy. On behalf of ISA panel students, I welcome all the participants to the fifth day of Limit Camp. Today's student lecture will be given by Aprameya G. Hebbar. He is currently pursuing BMath and is in his second year. His main interest is analysis. I welcome him to share his views on the topic calculus from the beginning. Thank you, Aprameya.
Thank you, Venkat. I will share my screen. Yes. Yes. So can you see my screen?
Yeah.
Yeah. Okay. Good evening, everybody. So in this lecture, we will be going through a short journey to the development of calculus. You will be seeing how calculus was developed by the giants like Newton, Jacob, Bernoulli, and Euler, as well as you will be seeing how there was a transition from intuition and towards the rigorous calculus that you will be learning in the undergraduate course. So we will begin with Newton. So Newton actually invented what we call as flexions, and so we will be seeing what these flexions actually are. So a flexion is, the definition is that it's an instantaneous rate of change, a gradient of a time varying quantity. So these were what made up Newton's early calculus. Okay. So this was the book that he wrote, De Analysi, which we'll be calling De Analysi, and this was the book that he wrote about whatever uh, the calculus that he had discovered. And this book actually shown the full extent of the power of his fluxional methods. So now we'll be seeing the first result that Newton gave early on, and that was the binomial theorem. So he found a simple way to expand, and his word was reduce the binomial expansion into series. So this was the expression that he gave. Okay, so I will now explain what these are. So this is any two real numbers, p and q are any two real numbers. This is a rational number, right? And here I will explain what these A, B's and C's are. And this and C was the old way to write dot dot dot, what we write today. So and C was up to infinity. So what these A, B, C are, these are exactly the preceding terms. I will explain this using an example. And what Newton thought, what Newton said that this series will do is that they will convert this expression, which is a binomial and hard to use expression, into a series which was easier. And he said that this would reduce a complicated expression into a simple expression. So now we'll demonstrate it with an example. So p equal to 1, q equal to x, and the power is minus half. So this was the formula. Now we put p equal to 1, q equal to x, and this term is 1. So we keep a, b, c's for now like that, and we would evaluate the coefficients. So now what a is nothing but the previous term, which is 1. Okay, so we put a equal to 1. And now what b is nothing but the previous term, x by 2 or minus x by 2. And so by putting that, you get this. And c is nothing but again the previous term, 3 by 8 x square, and putting that. So now we got a binomial expression. This was 1 by root over 1 plus x, and that was now reduced into a series, right? And so on. Now, if you have seen the infinite binomial theorem, this is the coefficient, this is minus 1/2. So minus 1/2 is nothing but, this is equal to minus 1/2 C2. Okay. And what is 3 by 8? 3 by 8 is nothing but minus 1/2 C3. So again, minus 1/2 C2, it is, what is this? This is minus half times minus half minus 1 by 2. So we call this theorem, whatever Newton invented, as infinite binomial theorem today. And that is for x, real x such that with absolute value less than 1 and m is any rational. So we have 1 plus x whole to the power m equal to 1 plus mc1 x mc2 x square and so on. So you would have seen this in finite case when m belongs to a natural number, in which this was a terminating series. But when m is a rational number, this does not terminate, because mck is always is never zero, so to say. So what is mck? Again, it is the same definition. Mck equal to m times m minus 1 times up to m minus k plus 1 by k factorial. Again, we can't write m factorial because m is a rational. So this is the generalization of the binomial theorem today. Binomial theorem, which was there for only exponents with natural numbers. So this is an important thing. So what we did, like the essence of this theorem is that wherever you see 1 plus x whole to the power m, you can write one this series, and this series is easier to deal because you have x square, which are all easy to handle than this term here. And now we are coming to the Newton's second discovery, and that is quadrature. Quadrature nothing means it's nothing but area under graphs. Area under graphs. And Newton was the first one to find area under graphs, like common graphs like y is equal to ax to the power m by n, which I have graphed here. So Newton actually had three rules to state, and he had kept it very as a secret, and he only revealed it to his close associates. So here are the three rules. The first rule is, if you have a curve y equal to ax to the power m by n, which we denote by AD. So this is the curve. Then he said that A is a constant, m and n are natural numbers. So he said that the area under region ABD, this region, this was exactly this quantity, an by m plus n x to the power m plus n by n. And you would recognize this easily by integrating, as we have learnt in calculus, by integrating a x to the power m by n from 0 to x. So to use another variable, I use t. So t to the power m by n dt from 0 to x. But in Newton time, this was a discovery, because now we'll see how Newton actually proved this. Now, what was his second rule? His second rule was, if a value of y be made up of several such terms, the area likewise shall be made up of areas which result from each and every one of those terms. For example, like you have a polynomial. So right, you can clearly find the area beneath a polynomial using this rule. And third rule was, but if value of y or any of its terms be more compound than the foregoing, that means the previous rules, it must be reduced to more simple terms. And afterwards, by the preceding rules, you will discover the area of the curve sort. For example, we want the area under the curve 1 plus x to the power half minus half that we just said. So what he said was, you convert it into series. So the first thing is you convert into series that we just saw. And now you can integrate term by term. Right, term by term, you can find the area and add up. So, like, how did he prove this without what was his original proof? So his original proof was that, actually, first of all, he didn't give the proof in the beginning in the de analysis. He said that an attentive reader only wants the proof of rule 1, and his derivation, blended geometry, algebra, flexions, and like it was like there is a twist of logic, as you will see now. So it proceeded in two steps. First step was that you assume the area under the curve to be y, and area under the curve y to be z of x, which is this expression. And then he proves that if a curve has this area, then that curve must be this, given by y equal to ax to the power m by n. And by we call this differentiating, but what he did was not actually differentiating, and we will see what he did. So let's proceed. To proceed, we need to make some notational simplification, and for that I would so first of all, like, we are assuming z of x to be equal to an by m plus n, and this is the area. Okay, so this is the area, and we would also we would assume that we'll take the power of n, and whatever the power that comes here, like an by m plus n whole to the power n, we are going to put it as c to the power n, and m plus n will substitute p, so that we get this expression. So now let's start the derivation. So first he took the curve. This is the curve y equal to ax to the power m by n. And like, yeah, feel free to ask any questions in between if you find something unclear. So he took AB to be x, a point x, and this is y, and y is equal to ax to the power m by n bd. And then this was set as O, and this is delta, this point. Like if you shift B by side to beta, then you D shifts to delta. And so now what he does is he constructs a rectangle. Okay, so let's take this area B beta delta D. This area he takes it, and this area, now he construct a V here like this. He calls it V, and such that this area is OV. So this is some area, like we cannot say what exactly is B beta delta D, and but he converts it into a rectangle OV. So now with this, you will be seeing that the area of A beta delta, the area A beta delta, this whole area, what is this? This is nothing but Z of x plus O, right? And but what is this area? This area is area of ABD, which is Z of x and plus OV. Okay, so now he takes power, like take the power of n, so that would become Z of x plus O to the power n is equal to Zx plus OV whole power n, and we assumed that Zx whole power n was equal to Cn xp, right? So that would become Cn x plus O whole p, and we would use binomial theorem here, Zx n plus nc1, which is n, and that is Zx n minus 1 OV plus nc2, right? And that is Zx n minus 2 O square V square plus so on. This is a finite sum. And if you would expand this, this is Cn xp plus n Zx n minus 1 OV. And I would just write, we can take O square term outside the rest of the terms, and there are some terms here. But this is also equal to. So again, you can expand this one also in binomial, as binomial series. So this is Cn xp. Again, these are finite series. Just make sure that you know it, because p is an integer. So Cn xp plus Cn xp minus 1 po, right? And so on. So now you will see that these terms cancel, and you can also cancel an O, right? Yeah. So now now Newton does like a a bit of confusing step, and he assumes now let O be 0. That means he just makes beta into B after this step. So if beta comes to B, then delta comes to D and V becomes Y, right? Right. So that makes Cn xp minus 1p is equal to n z of x n minus 1 y. So now you get what? Y equals to Cn xp minus 1p by n z x n minus 1. And if you just make some substitutions, like if you substitute back here, you will get the same thing, y equal to ax to the power m by n. So you saw here, like we don't know what he did, but he still proved that if it has an area of if it has area z of x, then the curve must be y equals to ax to the power m by n. So, but I've just written it again. But if you just observe that Newton first supposes that O not equal to 0, and he does calculation, and then he does divide it in one step also. He divides by O, and then suddenly in the next step he assumes O equal to 0. So this is a zero non-zero dichotomy, and this would trouble analysts for the next century. And we cannot say that he was wrong, because Newton was writing it at the beginning of the journey of calculus, and his time, like, this proof was groundbreaking, and his conclusion was indeed correct. So, like, we saw this is just this is just one power of one demonstration of the power of fluxion method. These are called fluxions, or like vanishing quantities that stay non-zero for some time and then go to zero. So we will see now another result by Newton, and he actually uses the rules of quadrature that he gave to find an infinite series expansion of inverse sine. And he says arc sine x, which is sine inverse x, and this is nothing but x plus x cubed by 6 plus this like you'll get these terms, and all have odd powers, x cube, x5, x7, x9, and like this was how he did. He uses area and some geometrical arguments to come up with this series. And with this series, with the series of sine inverse x, he finds the series of sin x by inverting it. So he gives a long procedure in order to invert it, and term by term he finds the series of sin x, and you would have come across this. Sin z is equal to z minus z cubed by 3 factorial plus z5 by 5 factorial. So basically, like Newton, Euler, Jacob, Bernoulli, they all had one thing in common. They were very good at series manipulation. So now we'll be saying goodbye to de Analysis actually. And actually Newton's De Analysis was a true classic of mathematics, belonging on the bookshelf of anyone who interested in how calculus came to be. It provides a glimpse of one of history's most tile thinkers at an early stage of his intellectual development. And Newton had combined infinite series and fluxional methods to push the frontiers of mathematics in new directions. So we just saw one instance of derivative. Now we will see what they thought of integral. Both Leibniz and Newton, they thought of integral to be an area under the curve and as an inverse of differentiation. So they also invented the integral calculus that are taught in high school today. For example, integration by parts, which Leibniz had discovered through geometric arguments, and he called it Leibniz transmutation theorem, and this was the form in which he had derived. And so basically what, like, the main thing is that they had an intuition that if you have a continuous curve, like continuous function, you can always find the area by integrating it. So so integration was mainly done for continuous curves and not for discontinuous curves as we know today. So yes, now we will be seeing Bernoulli's. Actually, there are like more than 20 mathematicians and scientists in the Bernoulli family, but the two main Bernoulli brothers, were Jacob Bernoulli and Johann Bernoulli, who did much to build it into the subject like we know today. So, for example, it was the Jacob who gave us the word integral, and they both worked together, the Bernoulli brothers, and they read Leibniz's paper, and they grappled with the dense exposition, fleshed out its detail, and then in correspondence with Leibniz and with one another, they provided coherence, structure, and terminology. For example, they made differential calculus and integral calculus, and so on. So now we will be looking at, like, they derived a lot of results, but we'll be looking at one result, that's Johann Bernoulli's integral 0 to 1 x to the power x. This is actually a very beautiful result, and Johann Bernoulli is known for his contributions to infinitesimal calculus, and for one more thing, he educated Euler. He was the tutor of Euler actually, and when Euler was young. So first of all, we'll be looking at Bernoulli's rule. The differential of a logarithm, no matter how composed, is equal to the differential of expression divided by the expression. So what he was referring to is that DLF is equal to f dash dx by f. So basically, we will be writing LF as Bernoulli did to write ln f of x, ln f of x. Right? We'll be writing this just because Bernoulli did. And so so basically, he's saying that rule for derivative, like d by dx of ln f of x is equal to, you can write it as f dash of x dx, f dash of x by f of x. Right. So you know this. Bernoulli gave this as a rule, and he was the first one to explain. Like people have doubt, saying dx, or sorry, x to the power p of dx is equals to x to the power p plus 1 by p plus 1 plus c. So what do you do if p equal to minus 1? So he was the first one to say integral dx by x is indeed ln of x. So again, this is nothing but ln x. We write lx because like Johann used to write it as lx. So now, first of all, before going to into the integral, we'll be looking at the graph of x to the power x and how he found the minimum of the graph of x to the power x. So here, the graph that you are seeing is the graph of y equal to x to the power x, and it has a minimum at m, and a general point is f x y, and this is a tangent, the line that meets here. So the tangent at f meets the x-axis at L, and this, yeah, so this LE is what is called a subtangent, right? So basically, we all find it. We all find the minimum of x to the power x by differentiating it. So you assume f of x equal to x to the power x, and then you differentiate it, and then you equate it to 0. But that was not how Johann did. So firstly, he took ln in both the sides. He assumed x to the power x is equal to y. Now he took ln, so x ln x equal to ln y. And by his own rule, so we have dy over y, differentiate both sides. And you can use a product rule here. So first, if you differentiate x, you'll get ln x in that term. And then by differentiating it ln x, you have 1 by x. X times 1 by x becomes 1. So what is y by le? So y by le. So this is actually the so what is y by le? Y by le is nothing but tan theta, right? This is if you assume this is equal to tan theta, which is slope of tangent, that is dy by dx. And so what was le? So le is equal to y dx by y by dy by dx, and that is 1 by 1 plus ln x. So you have just take this down, and you have y dx by dy, which is 1 by 1 plus ln x. So basically what he's doing is, this is a subtangent. This is called a subtangent. So the length le. So now what Johann did was that he said the least value occurs when the tangent line is horizontal. This is obvious, right? So when, like, that's what we use. So when the tangent line is horizontal, the minimum occurs, and when tangent line is horizontal, the subtangent is infinite, right? So that makes 1 plus ln x to be equal to 0. But now the problem came that E was not yet invented because Euler wasn't there. So he had to give a complicated geometric procedure for identifying the value at which 1 plus ln x equal to 0. Like he couldn't do, you can just take x is equal to e to the power minus 1. He couldn't do that because E was not yet defined. So therefore he had to give a big geometric procedure, uh, and so like his reason was too long to modern taste, actually. So this was one of the problem they faced, right? And yeah, you should note that ln was used much before, like invented much before than E was. So they knew to take ln, but they hadn't got this E. So now let's go to the integral. So if z is equal to ln, yeah, they didn't know E, but they had yet like they had defined that if z is equal to ln n, then n is equal to 1 plus z by z square by 2 factorial plus z cube by 3 factorial, and so on. So basically what they are doing is n is equal to indeed e to the power z, and they are writing e to the power z as 1 plus z square by 2. So they knew this, right? And so now if you put n is equal to x to the power x, so you get the series expansion of x to the power x, which is a bit complicated, and it's not a series expansion because we have ln terms here. And now in order to integrate, actually, in order to integrate x to the power x from 0 to 1, you need to integrate these terms. So you need to know what is 0 to 1 x to the power n ln x to the power n dx, right? So you need to know this. So in order to know this, what Johann did was to write out a table. He did integral dx is x, integral x lx is equal to half xx lx, xx means x square, so half x square ln x minus half square of x square, and so on. He wrote out an integral, and he said like you can continue on forever. So what that the main technique he used was recursion. So he would put this here and so on, so forth. Like he would use x square lx square to derive this. He would use x integral of x lx and so on. So like in modern the modern way to do is a reduction formula, which I have written it for you here. So integral x to the power m lx ln x to the power n. So we could relate this by via integration by parts to this one, where we have n minus 1 here, and here we have n here. So in this way you could also derive all these results. So after writing out a table, so he integrated it. So here he's assuming that with a series expansion, you can integrate each term and add them up, right? As Newton's quadrature did. So for the first term is nothing but x with 0 to 1 as limits, which comes out to be 1. The second one is integral 0 to 1 x ln x. And according to Bernoulli's tables, this is the antiderivative. And now if you put it, if you put 1, so you get 0 at the first term, you get minus 1 by 2 square. But if you put 0, so you have 0 times infinity here, indeterminate form. And this term goes to 0, no problem. So, but still, Bernoulli writes minus half square. And his reasoning is that all the terms, right, his reasoning is that all the terms in which are found Lx or any power of the natural logarithm vanish insofar as the logarithm of unity is 0. But this is clearly not so obvious, right? Because we what he's trying to say is that limit as I'm sorry, not n approaches to infinity, a small typo, x approaches to 0. Limit as x approaches to 0, x to the power m ln x whole to the power n is 0. But we need L'Hospital's rule. So this was Bernoulli's intuition, and he did not have a rigorous backing for this argument. So like this is one more instance where mathematicians used their intuition in deriving results. But in any case, like if you see the pattern, you get minus 1 by 2 square, and then the next term you get minus 1 by 3 square. So we obtain a very beautiful result, like 1 minus 1 by 2 square plus 1 by 3 cube minus 1 by 4 and so on. So like this is a wonderful series, and this converges so rapidly. Like the 10th term is 1 by 10 to the power 10. Like it's just contributing a thousandth of million part of unity into the sum. So after this, we'll be going to Euler, and Euler is the master of all of us. And you all know Euler, and he gave us the most beautiful equation of mathematics. And Euler was indeed a genius, and he wrote an introductio. We'll be calling Introductio in Analysis Infinitorum, which is a two-volume work, right? Which is a two-volume work, and that lays foundation to all the mathematical analysis that we do today. Euler gave us a lot of results. Like we cannot talk about Euler without seeing the amount of work that Euler has done with broad inexhaustible interests. He had a lot of interests, and he revolutionized mathematics, and he extended the boundaries of such well-established subdisciplines as number theory, algebra, geometry, even while giving birth to new ones like graph theory, calculus of variations, and the theory of partitions. In 1911, scholars began publishing his collected works in the name the Opera Omnia, and they faced a daunting challenge. Today, after more than 70 volumes and 25,000 pages of print, the task is yet not complete. They are still publishing. It's 70 volumes, so it's so much in one lifetime. He was almost equal to 1,000 mathematicians, I can say. And so we'll be seeing what Euler what the earlier mathematicians thought of a function. So we all know what a function is, but it was not so obvious. And in his Introductio, Euler starts with the definition of function, and he said a function of a variable is an analytic expression composed in any way whatsoever, the variable quantity and the numbers or the constant quantities. So he was saying like a to the power z, a plus bz, these are all functions. But this is indeed not a general definition, right? Because you can think of piecewise functions, which are they are not in any way analytic expression composed of the variable quantity. So he had to change it, and after a few years, he wrote that those quantities that depend on others, namely those that undergo a change when others change, are called functions. And this is the definition that we take up today. And this was a shift in the concept of functions, but there's a lot more to come, because this was how things that we take for granted today were not indeed so obvious to the mathematicians who discovered them. And with this, we'll now look at some beautiful results by Euler. And the first one is this integral 0 to 1 sine ln x by ln x dx is equal to pi by 4. And how he did this? Again, we use the series. That's the standard technique. So he, as we have seen, they already knew the series of sine, which was x minus x cubed by 3 factorial plus x5 by 5 factorial and so on. So he expanded the sine ln x into the series, and this becomes, so now one term ln x cancels out, so you are left with this. And now here Euler observes now, so therefore calculating this integral reduces to calculating integral 0 to 1 ln x whole to the power n dx. And so he would split the integral, and here he would observe that ln x whole to the power 2n is indeed 2n factorial. So this is actually a beautiful result, which we'll be seeing in the next few slides. So with that, what happens is this becomes 2 factor. This term becomes 2 factorial. So we get 1 by 3 there, and this term becomes 4 factorial. We get 1 by 5 there. So this is 1 minus 1 by 3 plus 1 by 5 minus etc. So this was a famous result, and which had the value of pi by 4. And this was indeed first discovered by Indian mathematician Nilakanta actually. And then Leibniz also had discovered, and independently Gregory, which this is actually known as Gregory series. And this gives the pi is here, pi is represented as an infinite series. So with this, we now go to one of the most important, the most awesome result, I can say, the spectacular sums. And why this came? Because Jacob Bernoulli had solved for many figurate series, but he could not find sigma 1 by n square, sigma 1 by n to the power 4 after all his efforts. By figurate series, we mean triangular numbers, etc., those with binomial coefficient. So indeed, Jacob had also gave the first proof why sigma k equal to 1 to infinity 1 by n is infinite. So indeed, this series, even though it goes so slow, it is actually infinite, and you'll be doing this in the exercises actually. And one can easily show that sigma 1 by n square is indeed finite. But what's the exact sum? And Euler, in one single theorem, found out all the series sigma 1 by n square, sigma 1 by n4, sigma 1 by 6, n to the power 6, and so on, and many others. So he found sigma 1 by n to the power 2k, n equals to 1 to infinity. So he found all of it in one single theorem, and we are going to look at that single theorem. So let's start. So now suppose that p of x is some function, and you represent it as a series 1 plus ax plus bx square plus cx cube and so on. And you represent it as a product also, 1 plus alpha 1x plus alpha into 1 plus alpha 2x into 1 plus alpha 3x and so on. So he says whether these factors be finite or infinite in number. And here Euler promises a rigorous argument using the differential calculus. So a side note which you should remember, which will be handy, is that minus 1 by alpha 1, minus 1 by alpha 2, etc. are the zeros of p of x, because if you put minus 1 by alpha 1 here, it becomes 0. So first of all, Euler applied the natural logarithm. So applying the natural logarithm to this and this, you get ln p of x. I'm writing in the sigma notation now. It is equal to k equal to 1 to infinity ln of 1 plus alpha kx. So now you can differentiate it, and that's what Euler did. So p dash of x by p of x, again this is the Leibniz rule, and he actually, this is an intuitive step. He exchanged the d by dx with sigma, and suppose let's say we can do that. So again, this is also, you can say, Bernoulli's rule or chain rule. So you get alpha k by 1 plus alpha kx. Now he would use this as a series. So this is the geometric series which you have, which you would have seen. You can take alpha k out and you get 1 by 1. And if you take this as minus r, so you have 1 by 1 minus r as 1 minus r plus r square minus r cube. And so putting minus alpha kx, you have alpha k minus alpha k square x plus alpha k cube x square minus so on. So like, what's the point of it all? So here comes. Now if you would distribute this sum, so you get the summing over the first term, you get sigma alpha k equal to 1 alpha k, and that goes to infinity. Next you would sum over alpha k square, taking x out. Next you would sum alpha k cube, and so on. And for notation, we'll represent this as s1, s2, s3, and so on. Basically, sr is sum of rth power of the roots of p of x. So with this, now we would use the second expression that was that we had defined. So basically, what happened is, this is p dash of x, right? And this was p of x, and this was the right hand side expansion that we had got. So transferring p of x and writing it as 1 plus ax plus bx square, and so on, we get this equation, right? Like, if you have any questions, you can ask in between also. So now we multiply on the right hand side. So multiplying on the right hand side, the constant term is nothing but s1. Now the terms with x are only 2, which is 1 times s2 here minus s2 here, which gives minus s2, and a times s1. So a s1 minus s2, and you can take the terms of x square and so on. Now these two series are both equal. So equate the coefficient. You get a is equal to s1, right? This is s1. A is equal to s1, and what is 2b? 2b is equal to as1 minus s2, right? 2b is equal to as1 minus s2, as1 minus s2. Now you can use a is equal to s1, so you get a square here minus s2. So s2 is equal to a square minus 2b. So again, using this, you can write sum of third powers of the roots as a cube minus 3ab plus 3c. So okay, but if you have studied polynomials well, you would see that sum of roots is equal to the coefficient of like, these are indeed, you can relate them to polynomials actually. So let's see. So now we are going to apply this result on this function p of x. So this is cos pi by 4x plus sine pi by 4x. Actually, Euler did a lot more with this theorem. But we are going to take a simple function here. So again, we know the series, right? What is the series? So this is the series of cos x, 1 minus 1 by 2 factorial into the argument square plus 1 by 4 factorial into argument 4 minus, etc. And we know the series of sine, which is x minus x cube by 3 factorial. I mean, whatever x, I put x naught. So plus x naught 5 by 5 factorial, which he has written here. So now taking up the, like, if you just clean it up a bit, you get 1 plus pi by 4x minus pi square by 32, which comes from here, and pi cube by 384, which comes from here. So this is basically the A, and this is B, this is C, and so on. Okay, so what are the roots? The roots are exactly, if you just check, like put this equation into 0, they are exactly minus 1 to the power n by 2n plus 1, the odd number, like minus 1 to the power n by 2n plus 1. So what does the lemma gives, the previous lemma which we derived? So what is S1? S1 is indeed A, right? S1 is A, S2 is A square minus 2B, S3 is this one. So now, wait, okay, so what is S1? S1 is sigma minus 1 to the power n by 2n plus 1. I'm not writing the limits, it's just 1 to infinity. So S1 is equal to A. What's A? Pi by 4. So he is getting the value of series here. So the first one gives this, equating the second term, this is nothing but S2, right? Equating the second term, you get pi square by 8, and so on. So with this, it's a nice exercise that with this you can find the value of sigma 1 by n square. Okay, like this gives us the odd, and you can you have even terms in this, and you can easily derive this result. This is a famous result from S2. So, but you can go on, right? You can find S3, S4, and Euler could find the values of all uh, S. So all S2n would give you the values of sigma 1 by 2, sigma 1 by 2k. So this would give the value of sigma 1 by 2k. So all these series in one lemma, right? So but what about sigma 1 by n cube, n equals to 1 to infinity? What about these? So basically he was very clever at like he, these are called, like, these are not theorems now. Like nobody uses these. There are other theorems actually. So these are unorthodox methods of summation. And and he said, what Euler said was that uh, like for these sigma 1 by n cube, he said they cannot be expressed by logarithms, nor by circular periphery pi, nor can a value be assigned by any other finite means. And this is true even today. We still don't know any analytic expression that would give us the value of sigma 1 by n cube n equals to 1 to infinity. And this is indeed called as Apris constant by Robert Apris. So like Euler's intuition was indeed really great, and he wherever he applied his intuition, he had applied them perfectly. So one more great result by Euler was the problem of extending n factorial. So we need, like, can you give like the problem was, can you give a analytic expression that when you input, like for example, let's say an expression s, let's say, can you give an expression f of s such that when you put s is equal to 1, 2, 3, you get 1 factorial, 2 factorial, 3 factorial. So this problem was posed by Daniel Bernoulli and Christian Goldbach in 1720s, and Euler wrote to Goldbach in 30 to announce his discovery, which is n factorial is equal to 0 to 1 minus ln(s) to the power n ds. So basically, if you would put let's say f of t to be equal to 0 to 1 minus ln t to the power, sorry, minus ln s to the power t dt ds. So then when you put f of 1, you get 1 factorial, f of 2, you get 2 factorial, and so on. But now you could think like half factorial, and you could define this to be f of half, right? So this sort of extrapolated the values of the factorial. And by an interchange of value, if you put t equal to minus ln s and use substitution rule, you get this integral here, and this is known as gamma of n. And this integral is 0 to infinity x to the power n minus 1 e to the power minus x dx. So in the exercises, you will be you will be proving the value of this integral actually. So one more
Which
example of
exercise are you talking about?
uh,
Which exercise are you talking about?
I'll give the PDF. I'll share the PDF after the lecture in the group. Okay. Yeah. So one more example of Euler's intuition. So Euler gave the value of this 0 to infinity sin x by x dx. And you would have seen a computation of this using the what is called as Feynman's trick, introducing e to the power minus tx here. But what Euler did involved complex numbers. And I would I want you to get a feel of this, because this involves a bit of complex numbers. So by taking the gamma integral and substituting, you get this integral here, which is just x to the power n minus 1. Instead of e to the power minus x, if you put a kx, you get this term here, k to the power n. So now I want to write this in red because this involves an intuition. So this is actually true for k in reals. Okay. But now Euler assumes that this works for complex numbers also, which is totally intuitive. Like this actually to do this you need something called as Cauchy's theorem that comes under complex analysis. But let's see. So after putting this, so now you can take the conjugates in this fraction, right? And take the real part of this expression. I'm just skipping the details, but I would like to just note like how Euler's intuition was indeed correct. Like even after doing such intuitive steps, he actually got the correct result. And here also he take like after getting this integral, he takes the limits as n approaches to 0, which is again intuitive, and he does some approximation, but he indeed comes up with such beautiful integral 1 by x e to the power minus px sine qx is tan inverse of q by p, which upon putting q equal to 1, p equal to 0 gives this result, which is indeed correct. But his steps involved a lot of intuition. Euler had such perfect intuition, like yeah. But we like you do this in undergraduation with in complex analysis. Like you need lot of stuff, lot of machinery in order to follow these steps. So now like one more instance of power like the prowess of Euler actually. So he lost his eye in the age of 33, and the other eye also he thought that it will be in the danger. But Euler said upon losing the sight of his right eye, now I will have less distraction. He was when he lost his eye at the age of 35, he was indeed writing a paper a week. Like he would just have his students sit around him, and then he would just say and they would write, and he could do big calculations all in his mind. Euler was indeed a genius. Even after losing his right eye, and like even after losing his eye, he was able to give so much contribution. Uh, and so at this point, we would like to uh, take a break actually and see what's this intuition thing that's coming here. So the calculus pioneers operated more on intuition than on reason. Admittedly, their intuition was often very good, with Euler in particular possessing an uncanny ability to know just how far he could go before plunging into mathematical abyss. So at this point actually like they did a lot of like they are the heroes. So like hats off to them. But at this point there came a critic, like the critic of there came a critic, and his name was George Berkeley. So he was actually a bishop he was actually a bishop. He was not a mathematician, but he said the further the mind analyzes and pursues these fugitive ideas, the more it is lost and bewildered. So let's see why. So he said, what are these flexions? They are neither finite quantities nor quantities infinitely small, nor yet nothing. So he's saying the example of O, which was in first not equal to 0, and then it became 0, and then it just vanished. So maybe not call them ghosts of departed quantities. So like this is like why what does he mean by this? So let me take you through a practical demonstration. So let's differentiate x to the power n, the basic question. So for a real x, you have this using binomial theorem, you can expand x plus h whole to the power n as x to the power n plus nh x to the power n minus 1. The x to the power n term cancels out, and you are left with first term is nx to the power n minus 1, and the second term is nc2 x to the power n minus 2 h to the power 1 because h cancels out here, and so on. So this is indeed a finite sum, right? So now obviously h is not equal to 0, right? Otherwise you couldn't have done so much in a single step. So but now up to this point h was assumed to be non-zero, a supposition, but then h suddenly becomes 0. That's how you take derivatives of x to the power n. So you would write then, okay, let h go to the 0, and you would put all other terms to 0 because they involve h, and only the first term comes to this is remaining, and you take this as a derivative. So Berkeley said, after all, if h is 0, we are forbidden to put it into a denominator. Like the argument totally collapses, right? Because first of all, h was not equal to 0, and then h equal to 0. When it is said, let the increments vanish, like like only a consequence of it is retained. How can this be retained when you already have a contradicting statement, right? So Berkeley objected that the second assumption was in absolute conflict with the first, and consequently negated any conclusion derived here. So like we So what's the problem here? Like why is it going wrong? It's because we don't have definitions. We don't have clear basic definitions. So we cannot have a definition like put first let h to be not equal to 0, then put h equal to 0. This is not a correct definition. So we need to like base analysis uh, in more clearer definitions, and that's what mathematicians were up to now. And the first thing they started deriving is like defining is limits. So it was D'Alembert who first proposed that calculus should be based on the concept of limit. He said that we will refer dy by dx as quotient f of x plus h minus f of x by h. As h, he used the term approaches. So let h approach 0, right? And he said that there is no use of infinitesimals nor vanishing quantities, and deserves credit for highlighting limits as the way to repair weak foundations of calculus. But we cannot say him as the founder of calculus, because he didn't actually, he sensed the right path, but he did not follow it very far. So then came Lagrange, and Lagrange gave a theory that let's just, like, we are doing infinite series all the time. Let us not use it as an output, but as a source. So he said that we would put f of x plus h as a series f of x, and then h times p of x, h square times q of x, and so on. And then you would recognize this term, right? This term as f dash of x. This term as this term by 2 factorial as 2 factorial times this term as f dash dash of x. Like how is he coming from here to here? It's just like you can take f of x plus h minus f of x over h. You get that to be equal to p of x plus h times qx, and so on. So all other terms will involve h, and when you approach h to 0, all these will just go to 0, and you'll get p of x. So but this theory failed. Why? Like, it's a good exercise to prove that this function here, this weird function, it indeed is differentiable at 0. That is, f dash of 0, f dash dash of 0 all exist, but all of them are equal to 0. And indeed f of 0 is also equal to 0, but the function is not 0 in the neighborhoods of 0. I mean, if you try to write this as a series, then all these terms are 0. For example, you put x is equal to 0, you have f of h, and you have that 0 plus 0 plus 0 plus 0. But f of h is not equal to 0, so you cannot write this function as a series expansion. So you cannot base calculus on this theory. And this function was indeed first given by Cauchy, who just totally destroyed the theory of Lagrange. And so it turns out that Cauchy was the first one to actually give the definitions of the limits similar to as we use today. So we are going to now look at Cauchy, and Cauchy is actually the France's greatest mathematician. And let's see what how Cauchy defined the limit as. So, like, the definition of limit that you will be seeing here is it's in English. Like, it's not in mathematical, but what you will be studying, it is just the mathematical form of what is written here. So it's totally described in words. When the values successively attributed to a variable approach indefinitely to a fixed value in a manner so as to end by differing from it by as little as one wishes, this last thing is called the limit of all others. So as little as one wishes means, so he's saying that suppose you want to define limit as x approaches to a f of x. So what he's describing is that you want to make this difference as little as possible, then where does this go? F of mod of like, can you actually make the difference between, if you want to define limit of f of x to L, can you make this difference as small as you wish? If you can, then this value L can be called as limit. And so, like, this is the exact definition, almost exact definition, which we take today as the definition of limits, except that we use epsilons here and deltas here, which I don't want to go into now because it's just it will confuse you. So we are going to take this as a definition for the rest of the talk here. So Yeah. So what was the definition of convergence? So basically, like so first of all, he said that this is a what is sequence of numbers. It is just nothing but an infinite so suppose you consider a sequence of numbers. Now he wants to define that these converge to L. So just to give you an example of here, since you are not so accustomed to sequences, let's look at the sequence 1 by n, right? So you have 1, 1 by 2, 1 by 3, 1 by 4, and you can see that this is 0.25 and 1 by 5, you can 0.2. It goes so small that you can say that it will go ultimately, and ultimately it will go to 0. So you want to define 0 as the limit of this sequence. So Cauchy gives the definition of that. He wrote, when the successive numerical values of a variable decrease indefinitely so as to become less than any given number. So if you can find make 1 by n so small, like I would give you 0.00001. Can you find an n such that 1 by n will be small? You can, obviously. You can take you can take n to be 10000 at the required number of zeros. This variable, that is this variable, will be called an infinitely small quantity. So basically an infinitely small quantity is nothing but 0. So here Cauchy is actually telling us that if you can make the sequence as small as possible, then that sequence converges to 0. So he gave the modern definition of continuous functions. He also gave the modern definition of the limit. Now this symbol actually has meaning, right? It's not take I not equal to 0 and then put I equal to 0. Now it has meaning. It has to approach. And these rotations were actually invented by Lagrange, the writing like this I and so on. So earlier mathematicians actually, had accepted certain results as true, because either they confirmed by intuition, like Euler or Newton did, or were supported by a diagram. If you can put a diagram and say, yeah, this happens, okay, then they would take it. But Cauchy was totally unsatisfied. He wants an algebraic argument. So Cauchy said it would be a serious error to think that one can find certainty only in geometric demonstrations or in testimony of the senses. And today we'll be looking at one such theorem, and that is the intermediate value theorem. So like this is the most obvious thing to eyes. So like if you have a function, let's say now with x0 is a point and x is another point, and this we are assuming that this is a continuous function, and suppose that f of x0 is less than 0 and f of x is greater than 0. So it is such an obvious fact that it should take 0, because we believe that continuous functions are those functions which you can draw. You can draw them without lifting the pen. So with such concepts in mind, this is such an obvious. But Cauchy was unsatisfied. He really wanted an algebraic argument. So this is the intermediate value theorem. Intermediate value property says that you should get an a. So you should get an a such that f of a is 0. So let's look at how Cauchy proved this. So how Cauchy proved this? So first of all, we fix m greater than 1. So now Cauchy wants like splits this interval. So the interval is x0 to x. This is weird because, but still we want to go with Cauchy, how he took it. So he splits the interval into m parts. So we are now first we are assuming that h is the quantity h is given by the length of this interval. Okay, so if you want to split this into m parts, so the first one will be x0 plus h by m. I hope you are able to follow me. Second one is x0 plus 2h by m, and so on. So the last one is x minus h by m. So these are the m parts. So now you consider the function values of function at these points of the graph. So this, and so on. Right. So at some point you get this, and here, and so on. So if you consider the value f of x0, x0 plus h by m, x0 plus 2h by m, and so on, now this will be negative, 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 and at some point it will be negative, and the next one will be positive, right? So this must happen because we are having a finite number of points, and some are negative, some are positive. So there must be a point in which the sign changes. Okay. So with this, now we would want to recognize that point. So for some n1, f of x0 plus n1 h by m is less than 0, but f of x0 plus n plus 1 h by m is greater than 0. So now this is such an interval, and now we would want to repeat this procedure in that interval. So you take x1 to be this, and capital X1 to be to be this point. So now if I just zoom in here, now it's x1 here, x1 here, and function's value at x1 is negative, function's value at x1 is positive. Like obviously if x1 function's value at x1 is 0, we are done, nothing else. So we are supposing that it's not in x1, right? So with this, now you again split it into, now this time you again split it into m more parts. So now we consider the function value at x1 plus h by m square, x1 plus 2h by m square, and so on. Right. So now again you will find x2 here and capital X2 here, such that function value at x2 will be negative and positive. If it's 0, we are done. So suppose it's not 0, then you will find small x2 and capital X2. So now again you will find such an x2, which we would want to denote it like this. So in this manner, if you continue, you would find x1 capital X1, x2 capital X2, x3 capital X3, and so on. So you would obtain a sequence like this, right? So this part is an increasing sequence, and this part is a decreasing sequence, right? So now it's intuitive that if you have an increasing sequence, decreasing sequence, and like the difference between them, the distance between them are vanishing, like they can be made as small as possible, then you intuitively take that they will converge to the same point. And that's what Cauchy did. So he took limit xn and limit xn to be the point A. So obvious, now you can easily show that f of A is less than 0 and f of E is greater than or equal to 0. So with these two, you get f of A to be equal to 0. Why f of A is less than or equal to 0? Because the function's value at each point is less than 0, and here the function's value at each point is greater than 0. So this can be at most like it can be at most negative, non-negative, and this is like not positive. So with this he proved that f of A equal to 0. Again, I would like to stress here that whatever that I have written in red, this is indeed not an obvious fact, and this requires what we today call completeness property. So completeness property, like how are you sure that a decreasing sequence will converge to a point? It's because that R is complete, and this you will be studying in your undergraduate courses actually, and this is one of the fundamental properties of R. So word about Cauchy's work, and to name a few more like contribution, the Lagrange mean value theorem, which you studied today, it was first given by Cauchy, and he also proved the fundamental theorem of calculus, which is a part of calculus course, and he gave two convergence tests, which is very famous, and even which is taught today also, the root test and this Allen-Waller test, and his complete works, which are now published, come in 27 volumes. So like Euler, he did a lot of work, and there are so many results that are named after Cauchy. Like you can just Google the results named after Cauchy, and you will find so many. And all of us that came after Cauchy are his disciples, because calculus begins with, like, analysis begins with Cauchy sequences. So we are all following his work actually. So one more thing that he gave is this, like you could split integrals. For example, integrals were did earlier, as I had said, to only continuous functions. Now you could split integrals into those functions which have finite points of discontinuity. Suppose that f is discontinuous. That means suppose f is say like this here and suppose here. So now Cauchy said that you could still integrate these functions and write f of x dx from a to b, let's say. Then you could write it as a to k1 f of x. Now in this interval, f is continuous, and then k1 to k2 f, and so on, and up to kn to b f, right? So with this, now the realm, like the realm of functions which can be integrated, went from continuous to those with finite points of discontinuity. So we need to note the word finite. What happens if if a function has infinitely many discontinuity points? And clearly, can there be, first of all, And actually, it turned out that Dirichlet was the first one to give such a function, and this is known as Dirichlet's function. And here one supposes, let's look at what this function is. One supposes that phi of x equals a determined constant c when the variable x is rational, and another constant d when the variable is irrational. So basically, phi of x is equal to c if x belongs to q, and d if x is not in q. Right? So we'll be seeing that this function is indeed discontinuous at infinitely many points. So basically, the function is infinite, impossible to graph because of the thorough intermixing of rationals. You can find rationals between rationals and irrationals between rationals also. So the function continuously jumps back. At one rational, it's c and then d, c, d, c, d, c, d. So you cannot, like, if you want to like imagine a graph, it's like something like this. So it's totally, it jumps, so like it jumps continuously from c to d, c to d. So we'll be taking c equal to 1, d equal to 0 for like simplicity. So if you like wonder, can this be written in a single statement? Yes, it can be, and this is the single statement. Phi of x equal to limit m tends to infinity, n tends to infinity, this thing cos 2n m factorial pi x. And when x is rational, this comes to be 1, and when x is irrational, this comes to be 0. So this is just for, you can just try to solve this limit actually, and indeed find out that Dirichlet's function can be obtained like this. So where is it continuous? The answer turns out to be nowhere. Like there is no point in which it is continuous. So all you have to do is to consider the Cauchy's definition, right? So if you like, as I approaches to 0, this value jumps from, like, this value can be c, and so if x is, indeed x plus I is rational, this value is the value of the difference is c minus d, and if it is irrational, then it is 0 when x is irrational. If you assume x is not irrational, then phi of x has value d, and this can be c or d. So the difference oscillates between 0 and c minus d. On the other hand, if x is rational, then you can easily see that this term will be c, but this term can be d or c. So again, this oscillates between 0 and d minus c. So that, that does not come and sit anywhere, right? So as Cauchy's definition of limit said that it should come and approach somewhere. It's not approaching anywhere. It's just jumping up and down from 0 to c minus d or d minus c. So the answer turns out to be nowhere. So Dirichlet demonstrated two things. Arbitrary function can have teeth in it, and Cauchy's approach to integral totally fails. Like there could be functions which which cannot be, like, which have infinitely many points of discontinuity, and you cannot you cannot make them integrable by Cauchy's definition. So integration could be recast so as to not restrict mathematicians to integrating continuous functions or those with only finitely many discontinuity points. So we need to extend this, realm of functions which are realm of integrable functions. So again, the definition of integral was still not yet so concrete. So to make that came Bernhard Riemann, and Bernhard Riemann was the first one to define an integral in a different way, so as to allow lots of other functions to get integrated. And this was a concrete definition of integral, like not like area under the graphs, etc. So let's see, what is one to understand by the integral. So first of all, we would like to partition the interval AB into points, and that partition we want to call x1, x2, and so on up till xn. Xn minus 1. So we would take this to be xn and this to be x0. So, and the delta I is this is delta 2, this is delta 1, and so on. So delta I is the difference between the successive points in that partition. So taking this partition, we define what is called as a Riemann sum. So this summation is called Riemann sum, and epsilon is between 0 and 1. This was the definition Riemann gave for Riemann sums. And let's actually, in order to get some intuition about this Riemann sum, we are going to see how it is related to areas. Okay, so this is the Riemann sum, And with this graph, I would like to show you how this Riemann sum actually approximates the area. So suppose that this is your x1, right? So we are multiplying delta I plus 1, that is delta 1 times f of x1. So we are indeed actually taking this area. And that x1 can be anywhere in this interval, right? Like you can take any x1 and then make a rectangle, and the point where it meets, right, that's the first term of this integral. So you are taking some points and then just making rectangles and taking the area. So this actually is again, I want to say that this is dependent on what? The partition P and the epsilon i's, right? The epsilon i's, and that's all. Yeah, so this is dependent on two things, and f obviously. So with given a partition and epsilons, you can make out a approximate area. Now Riemann defines an integral in this way. If the sum has the property that however the delta k and epsilon k are chosen, it becomes infinitely close. Again, these words will be made rigorous, like are now rigorous, but when they gave, they write things as infinitely close and all. So if it comes to if it is infinitely close to a point a, to a number a, as delta k become infinitely small. Okay, so we want to make the differences between the points at the partition infinitely small, so much smaller. Then a is called as the value of integral. If the sum does not have this property, then we say integral has no meaning. That means integral is not defined. So now Riemann gave a property. Riemann gave an integrability condition saying that if this and such happens, then the function is integrable. So again, I want to discuss it very briefly about how Riemann gave. So first of all, we'll be defining what are type A intervals. So given a partition and where so let's suppose this is a partition. So such that each interval, again, I want to stress here, each interval is less than d. This will be needed. So every delta I, or you can say maximum of all delta i's, that is less than d. Then those intervals in the partition where oscillation of f exceeds delta were called type A intervals, and others were called type B intervals. So uh, just to show you what are type A intervals. So let's suppose that sigma is this one. Sorry, it's a sigma. Yeah. So sigma is this. I mean, if you put it sigma as a length, this sigma is this number. So now, if you see a to x1, what is oscillation? Oscillation means uh, the 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 total maximum of f minus minimum of that function in that interval. So the oscillation is this much. So clearly that's greater than sigma. Is it? Yeah. So clearly that's greater than sigma. So next, if you take the interval x1 to x2, again the oscillation is much more than sigma, right? So this is a type A interval. Okay, this is a type A interval. And if you take x2 to x3, the oscillation is only this much, which is less than sigma. So it's not a type A interval. So if you take x3 to x4, yes, it is a type A interval because oscillation is this much, and x4 to b is not a type A interval. So what we do is we let s of sigma, given a sigma, s of sigma, to be the combined length of type A interval. That is basically s of sigma is the sum of all type A intervals. So if you would sum the type A interval, you have x1 minus a, right? The length of all type A intervals, x1 minus a plus x2 minus x1 and plus x3 minus x4. This is s of sigma for this given sigma. So with this, Riemann proved an integrability condition like this. So integral AB exists if and only if for any sigma greater than 0, the combined length of type A intervals can be made as small as possible as we wish by letting d approach to 0. That is, in other words, you can make limit d approaching to 0 s of sigma. So I want to give an I don't want to give a proof here, but I would like to give an intuition. Suppose you fix a d, okay? So and you take any interval, any partition of a to b. Now, can you make s of sigma as small as you wish by taking such partition? Okay, and then suppose given any so can you make s of sigma as small as possible by taking d as less as possible. As d approaches to 0, just think of dependent and independent quantities. Here you fix a d and then you fix a sigma, or for any sigma. So you fix a d and then you make s of sigma as small as possible. So by taking d as small as possible, approaching d to 0, the s of sigma should also go to 0 for any sigma. Okay, so in geometric terms, right? In geometric terms, the idea is that in order for a function to have a Riemann integral, its oscillations must be under control. That means a function that jumps too often, too widely, cannot be integrated. From a geometric viewpoint, such a function would have no definite area beneath it. So to just demonstrate this one, we will check if Dirichlet's function is indeed integrable. So for this, I would like to choose sigma to be c minus d. Again, phi of x is c when x belongs to rational, d if x is not in rational, right? So now let us fix sigma to be mod of c minus d by 2. What do we mean by this? Let's I'm going to make just a graph. So this is how phi of x may look, and let's take 0 to 1 here, right? It's just oscillates. And what is my sigma? If so, this basically this is c minus d, mod c minus d, and I'm taking sigma to be c minus d by 2, which will be something like this, right? So now take any d as you wish, right? Any d, like fix any d. Now if you consider a partition with intervals like intervals having width less than d, what will be s of sigma? Every interval is a type A interval because oscillation is more than sigma. So no matter what partition you consider, every interval is of type A. So s of sigma is 1 for every sigma. Every sigma obviously less than mod c minus d by 2. So basically this is not approaching 0, right? We wanted limit as d approaches to 0, sigma s of sigma approach to approach to 0. But s of sigma is always 1, so it's not approaching 0. So clearly phi is not
Could
a,
you read this once again?
yeah, okay, yes. So did you understand Riemann's integrability condition? So basically what
I
he's
actually
doing,
did not.
okay, so see, so basically given a d, let's say you have a d, right? So this is the Dirichlet's function. Okay, so this is I'm just writing it so that you can understand. So given a d, so now what we do is, let's say you put s of sigma to be this. So you understand, right? Sigma is only this much, correct? So this is mod d minus c, and sigma is mod d minus c by 2. Yes. So now what is s of sigma? It is the sum of all type A intervals. What is type A interval? So you fix any partition. Okay, you fix any partition. If so you consider the first partition. You ask yourself, is the oscillation greater than sigma? So yes, the oscillation is greater than sigma, right? So let's say x1, x2, and so on up to 1, xn, right? So what about first interval? Yes, it is type A. So what is the length of interval? x1 minus 0. Okay. What about second interval? Again, the oscillation is maximum is d, minimum is c. Oscillation is more than sigma. So yes, it is also type A interval. So you sum them, x2 minus x1. And then what about third? Yes, it will be every single interval that we have in the partition are all type A intervals. So you are basically summing these lengths. Okay, from 0 to 1, you are summing all these lengths. So what is this s of sigma, which is the sum of all type A intervals? It is nothing but 1, right?
Yes.
Yes. So with s of sigma as 1 for any sigma, like for this sigma, so for integrability, we need every sigma to be, for every sigma, s of sigma should approach 0. But for this sigma, we found out a sigma such that s of sigma is 1, which is not approaching 0. Clearly, Riemann's definition is wrong. Like Riemann's definition is not applicable, or in other words, this function is not integrable according to Riemann's definition. Okay, so and as a definition says, this has no meaning. So basically, it's like the gist of everything is we found a function which is infinite, which has infinite discontinuities, but is not Riemann integrable. Okay, so basically, I think like people thought that every function is integrable in the beginning because every function seemed like a continuous function. But Dirichlet was the first one to say that you have a function which is so bad that it's not integrable. So now this makes us ask a question: how bad? Like how bad, or in other words, just how discontinuous can a function be and be still integrable? Like, can you have a function? So we already saw a function which has infinite discontinuities but is not integrable, right? So is there a possibility that a function has infinitely many discontinuities but is still integrable, really? So that means that you have a discontinuity at every point of, let's say, 0 to 1, and but it still has an area under the graph. Or to make it more precise, so we want to let df to be the set of all discontinuities. Means we take in all those points at which f is discontinuous. So in the case of Dirichlet's function, what is d phi? D phi is basically 0 to 1. It is discontinuous at every point, right? So if df is a set of all discontinuities, then let's take a bounded function. Then the bounded function is Riemann integrable if and only if df is dash. Like suppose it is Riemann integrable, that is, it has an area under graph for now. So what can you say about its discontinuities, the set of discontinuities? Basically, you cannot say that it is, can you say that you cannot say that it should be 0 or phi? Why? Because we know functions that are discontinuous yet integrable, right? You can take piecewise integrals that we saw. So one thing now, for now, we could say that the answer might be finite, but Riemann himself gave a function which has infinitely many discontinuities, yet it is integrable. So this answer is also not wrong, because this in this direction, Riemann has a function which has infinitely many discontinuities. So basically, what's the answer? So this was the question which would mesmer, like, it would confuse the mathematicians in the next century also. And that question was this, and like, everyone believed that the blank would be filled by some kind of smallness. Like, you want that to be small, not too small to be finite, not too big to be infinitely discontinuous, not finite, not infinitely discontinuous, something between it, some condition. And whoever would bring that whoever would bring this answer would make a big splash. Like there, now we are connecting what? We are connecting two concepts. We have continuity here, we have integrability here, we are connecting it. So we want the answer of this question, and the answer was provided by Henri Lebesgue, and it was this person in the photo here who actually found the answer to this problem and built a theory which is now called as measure theory, upon which we can do the calculus rigorously. And he gave the answer, and he became very famous. And now we have concepts called as Lebesgue measure in order to classify the sets. Like basically, he gave a measure to the set. So he said that a measure of sets of such and such can come and sit here as an answer. So I would like to end our journey here. I suppose that I have given some motivation to you and ignited some curiosity in you. We saw in this presentation that there are two aspects of mathematics, intuitive and rigorous, which has to support one another. You cannot be intuitive. You cannot be if it is too rigorous, we cannot understand it because we need some intuition. So again, we also saw that it takes years to build definition of a function, a definition of a limit, definition of integrability, and we cannot just say that we are actually we are taking it for granted. And we also saw that to get clarity in a definition, it takes again a lot of hard work. In order to understand a definition, it takes a lot of hard work, and without clear grounding, you could just go into deep waters. So now you have some new things in your bag of techniques, and the first thing is expansion into series. So I'll be giving a problem set in which you will be seeing some applications. So like we just did some applications, right? Just finding integrals, or finding finding limits, etc. But you will be seeing a lot of application of this series. And when you enter undergraduate courses, and you will see that how this is actually made into made rigorous by introducing concepts such as power series. But in the problem set, there will be an informal discussion only. And uh, although we saw, like, only non-rigorous methods in this talk, you will be introduced to them rigorously when in the real analysis. But I would like to make a point that it's always interesting while reading mathematics to look into the history of how it was developed. Uh, you should go and read books about how it was actually discovered. So we just saw how difficult it was to even you know find put up a definition of limit, and a lot of things were done before it, and how you should have, like, how they used the intuition. So it increases your, like, by looking. So, like, just Google it, when did Riemann like gave the definition of integral. It will just increase your interest to read, and it will give you motivation. So I would like to give some references here. William Dunham has a lot of books on such history, and the first one is the Calculus Gallery, and the second one is Euler, the master of us all, from MA, and the third one is Journey Through Genius. This is also a great book. And then E.T. Bell, Men of Mathematics. This is a really great book which every one of you should read. And then finally, there is a website which has more than, like, biography of nearly every mathematician, like more than three, like many. This is like, in this website, like, it's very motivational, and it explains their life. You'll get very much motivated if you read the biographies from this website, actually. And finally, Wikipedia. Yeah, so thank you very much. So if you have any questions, you can ask.
Can you please repeat the proof of the IVT?
Okay, yes.
IVT, the way Cauchy did it.
Okay, yes. So yes, so we are going here. Yes. Okay. Wait. Yes. So okay, I will wait. Before going it, I'll just have a new slide here. Yeah, 1 second. Yes. Let's close. Wait. Stop share. And then just escape. Yes. So. Yeah. Share. Yes. Yes. So basically, first of all, what he does. So he has x naught here and x here. So it, first of all, we assume that f of x naught is less than 0. We assume that f of x naught is less than 0. Okay, and f of x is greater than 0. So now he partitions this interval into m m smaller intervals. So basically, this whole thing is
M is integer, right?
Yeah, m is an integer greater than 1. So for example, let's say m is 10, right? That is better. So if m is 10, what happens? So basically, this whole thing is h. Okay, so this one is h by 10, and so on, right? You agree? So what is this point? This point is x naught plus h by 10. This point is x naught plus h 2h by 10, and this point will be x plus h x minus h over 10.
X minus.
Yes. So now, obviously, now if you see, there will exist some some x naught plus n1 h by 10, such that at that point this will be less than 0. If it is 0, we are done, right? We want to show there exists a such that f of a is 0. We want to show the existence of a.
Yes.
So if f of x, if there exists some, like in this partition itself, there exists a point in 0, we are done. Suppose not. Now you will find that this is less than 0, but the exact next one, x naught plus n1 plus h, by 10, this point it is positive at this point.
Means you're saying that there will exist one means
Yeah, there has to
n1h.
exist. Yes, there has
N1h,
to.
then the next point will be means positive.
Yes, n1 plus 1 h.
Yes,
So like at some
like
point you
this.
have less than 0, and the next point you have greater than 0. So now if you zoom in, you have the condition, like the proof is really beautiful. Now he takes it as x1 and x1. So now the case reduces to, like, the big interval reduces to this small interval x1, and x1 to capital X1, right? So now again he partitions this interval into 10. So what happens is that, like, this whole thing was h by 10, right? So what is this one? H by 10 by 10, which is h by 10 square, or h by 100.
100.
So now you consider these values: x1 plus h1 h by 100, x1 plus h by 2 h by 100, and so on up to capital X1 minus h by 100. Now you will again find some n1 here. You denote it by x2 capital X2. So what happens is you had initially x0 and x0 here. Now you get, first of all, you get x1 x1, x2 x2, and so on. Right. So again, how do you know that they can be like the difference can be small? Just you can just check here. Like, the difference at the second stage was h by 100. It's like
Yes.
the difference at nth stage will be h by 100 power n, which is approaching 0. It's becoming small and small and small and small. So at some point, like, this whole thing will be small. So he's here assuming that it will go to a. Okay. So now,
it's not really rigorous, right?
yeah, it's rigorous up to this point, but not at this point. So where the rigor fails is, how can you assume an increasing function to be approached to a limit? And this concept is known as completeness. It actually happens so because R is complete, and that you will study why. R is indeed R. The completeness of R is making this property true.
It's getting closer and closer. How do we write that in mathematical language? Means closer and closer, and it approaches
Yeah,
that
so
0 point.
So that takes you to the first lecture in analysis, actually. So what that means is, so let's say f of x approaches to L, okay, or let's say at
Using
this
epsilon
point,
and delta.
yeah, yes. So xn minus a. So the difference
We
between
have to
this,
define a sequence.
so the difference, you can make it as small as you wish. When you take as large n as possible, for example, you take x 1 lakh, then that will become so small that you can just make it, let's say less than 1 by 10. So you will say, I'll take terms more than 1 lakh, x 1 lakh, and so on, so that difference will be less than epsilon. So this is the epsilon delta definition, which came much later. But if you see, this is just like, this is parallel to the wording of Cauchy in his definition of limit.
Means if the addition means they should approach to a same limit. Yeah.
Yes. So they will, no. First of all, this will approach to a limit. This will approach to a limit. They will approach to the same limit. See, he's only assuming this will approach to a limit. This will approach to a limit.
Which two
They must,
sequences can write as sequences? That's what I'm saying. I want to see
so
the sequences which are approaching.
yeah. So that is small x1, small x2, small x3, and so on. Big x1, big x2, big x3, and so on. So if they both approach, they must approach the same point.
Won't they affect like in n1 and 2? Won't this depend on that n1 and 2? I mean, h is constant, fine, but
Yeah, so like h is constant. So x1 is dependent on n1. For defining x2, we used n2, and so on. So here also we have like n2 plus 1. We used n1 plus 1 here.
yeah, but won't it depend on that n1 and 2? That's what I'm saying. The limit.
It would but yeah, here again, a does not depend on m, right?
Okay.
That's
A
the
doesn't
thing.
depend on m. Of course, it doesn't depend on m.
Yeah, so if a doesn't depend on m, a doesn't depend on n1s, right? Like you see, n1 and n2 are just coming. Like, there is no, I don't think, I have not thought about dependence, actually. So like, you defined a partition, you got some n1, got some n2, and then so you took x1 and capital X1.
We can just take at a means n1 and I don't know. It would approach to a limit. It's obvious, but
So yeah, you could partition it anyway. Like, this was just standard partition, just taking equal intervals. Basically, you could just partition it anyway, find 2 points, again partition it anyway, find 2 points, again partition it anyway, find 2 points, and just take those points, you will approach to a limit. That would also be done. But again, you have to make such that the partitions are becoming finer and finer. Like it's happening here. The partition is at the n step, h by 10 to the power n is a partition. But again, this is not like this. This is a valid proof, but
The m
this is
won't
not a problem.
it won't depend on m. It means it would be m power n. Yeah.
Yeah,
Be m
yeah,
power
it
n
would be, yeah,
for all m.
yeah.
For
But
all m, but
assuming
the,
m greater than
so
1,
the
it would
sequences would be defined like x naught plus, I mean the points. Yes, like
yes,
on the right hand side, well, left hand side would be defined like x naught plus nkh by m power n, something like that. Yeah,
yes, m power k, yes.
m power k. But how will I say that the nk by m power k would like tend to a finite limit? The limit should exist. Yeah,
Okay. So if you see nk is less than or equal to m, greater than or
well,
equal to 1.
yes. M is the number of partitions. Yeah, yeah,
Yes.
yeah, yeah.
So the partition, like the number, the like it's nk partition, it will be between 1 to m. So clearly, you can just share one of these and make k minus 1, it will still work, right? This is less than 1, this term, and
Yes.
1 by m to the power k minus 1 approaches to 0. So basically, like if you want the exact
But it
definitions,
would be a non-zero limit, right? It would be a non-zero limit. The nk by m power k minus 1, it would be a non-zero limit.
yeah, it would approach to 0. Like, I mean, this part approaches like, yeah, okay, yeah, yeah, I get it.
Because a is not x0, right? A is not x naught.
No, a is not x naught.
Yes, that's what I'm saying. So it would
Sorry,
approach to a
I mean
non-zero
here
limit.
I have to put, like, it's not, no, even this definition is also wrong. Like, you have to put, not sure, no, you'll get summations and all, like you'll get n1. So basically this is n1, and then you will get here x naught plus n1 h over 10 plus
Yeah, yes,
n2
yes.
h
N1
over
h.
10 square plus n3 h over 10 cube and so on. This
So
is
that there would
x.
come a series. So that, how would that converge? Okay,
Uh,
okay. You just said that it's less than
no,
that.
like don't take the series. Like we are defining a sequence.
No,
Yeah.
no,
So
no. I'm just talking about the convergence of the series.
yeah, convergence of the series.
Okay, that can be done by comparison, right? Means
Yeah,
geometric
yeah,
series will come
yeah,
here. So
yeah. So all of these are less than
in
10.
case of m greater than 1, it would also take place.
Yeah. So you can just take out the h, and then you have n1 by 10, n2 by 10 square, and so on. So it's a geometric series.
No,
By
no,
comparing
it
it,
will be
you can make it less than.
h plus h by 10 plus h by 10
Yes.
cube, something like that. Yeah. Thank you, sir.
Yeah. Yeah. Any other questions?
Yep. Please be free to ask questions. So we'll wait till 7:30. If there are no questions, we'll end the meeting.
Yeah. You can ask any questions.